18.5 Macroscopic Description of an Ideal Gas. In this lecture, we will explore the macroscopic properties of gases. We will begin by comparing the characteristics of gases to solids and liquids. From there, we will define the ideal gas model and explain how to measure the amount of a gas using moles. This leads into the equation of state for an ideal gas and the introduction of two important constants, the universal gas constant and Boltzmann's constant. Finally, we will look at how these principles apply to real-world situations while clearing up some common misconceptions. When we talk about volume expansion in solids and liquids, we typically use an equation where the change in volume is equal to the average coefficient of volume expansion times the initial volume and the change in temperature. This assumes the material has a fixed, standard volume to start with. However, gases are fundamentally different because their interatomic forces are extremely weak or even non-existent. There is no equilibrium separation between atoms, meaning a gas has no inherent volume. Instead, the volume of a gas depends entirely on the size of the container holding it. Because of this, we do not use change in volume in our equations. We treat volume itself as a primary variable. To simplify the study of gases, we use the ideal gas model. An ideal gas is defined as a low-density gas, where the relationship between its properties is straightforward. We make two key assumptions in this model. First, we assume that gas molecules do not interact with each other except during brief collisions. Second, we assume the actual volume of the molecules themselves is so small that it is negligible compared to the total volume of the container. While no gas is perfectly ideal, this model is incredibly useful for predicting the behavior of real gases at low pressures. The image on this slide shows a gas confined in a cylinder with a movable piston, which allows us to change the volume for experimental observation. When measuring the amount of a gas, we use a unit called the mole, represented by the letter N. 1 mole is defined as the amount of a substance that contains Avogadro's number of particles, which is approximately 6.022 times 10 to the power of 23. To find the number of moles in a sample, we take the mass of the substance and divide it by its molar mass. Molar mass is simply the atomic mass found on the periodic table expressed in grams per mole. For example, helium has an atomic mass of 4 atomic mass units, so its molar mass is 4.00 grams per mole. The ideal gas law is the result of several experimental observations. Boyle's law shows that when temperature is constant, pressure is inversely proportional to volume. Charles's law shows that when pressure is constant, volume is directly proportional to temperature. Gay-Lussac's law shows that when volume is constant, pressure is directly proportional to temperature. We combine these into a single equation of state, which says that pressure times volume equals the number of moles times the universal gas constant times the absolute temperature. This equation allows us to describe the physical state of a gas sample by relating these 4 variables. The universal gas constant, known as R, is the same for all gases as their pressure approaches 0. The value we use depends on the units involved. In standard international units, R equals 8.314 joules per mole Kelvin. If we are working with liters and atmospheres, the value is 0.08206 liters atmospheres per mole Kelvin. An interesting benchmark to remember is that at a standard temperature of 0 degrees Celsius and a pressure of 1 atmosphere, 1 mole of any ideal gas will occupy a volume of 22.4 liters. We can also express the ideal gas law in terms of the total number of molecules, represented by A capital N, rather than the number of moles. In this version, pressure times volume equals the total number of molecules times Boltzmann's constant times the absolute temperature. Boltzmann's constant is calculated by dividing the universal gas constant by Avogadro's number, resulting in a value of 1.38 times 10 to the power of negative 23 joules per Kelvin. We use the subscript B to distinguish it from other physics constants, such as spring constants or wave numbers. Let us look at a real-world case study involving a shaken champagne bottle. A common misconception is that shaking a sealed bottle increases the internal pressure. In reality, as long as the temperature remains constant, the pressure inside a sealed bottle does not change. What shaking actually does is displace carbon dioxide gas from the space above the liquid into the liquid itself, where it forms tiny bubbles on the inside walls of the bottle. When you open the bottle, the internal pressure suddenly drops to atmospheric levels. This causes those trapped bubbles to expand rapidly and violently, which expels the liquid from the bottle in the famous spray we see in the image. In this example, we calculate the pressure change in a heated spray can. We start with an initial pressure of 202 kilopascals at 22 degrees Celsius, which is 295 kelvins. If the can is heated to 195 degrees Celsius, or 468 kelvins, and we assume the volume remains constant, we can use the ratio of pressure over temperature. By multiplying the initial pressure by the ratio of the final temperature to the initial temperature, we find the new pressure is 320 kilopascals. This significant increase illustrates why spray cans are a serious explosion hazard if thrown into a fire. What if we want to be more precise and include the thermal expansion of the steel can itself? Even though the can is solid, it will expand slightly when heated. Using the linear expansion coefficient for steel, we can calculate that the volume increases by about 0.71 cubic centimeters. When we factor this new volume into our equation, the final pressure comes out to 318 kilopascals. This is only a 0.6% difference compared to our previous calculation. This shows that while the expansion of the container does happen, its effect on the gas pressure is minimal compared to the effect of the temperature change itself. To summarize what we have covered, remember that gases do not have a standard volume and will always expand to fill their container. The ideal gas model is a powerful tool that assumes molecules do not interact and have negligible volume. This behavior is described by the ideal gas law, which can be written as pressure times volume equals the number of moles times the universal gas constant times temperature, or using the total number of molecules and Boltzmann's constant. Real gases follow these rules closely at low pressures. Finally, always remember to use absolute temperature in kelvins for all your calculations. We conclude with a few review questions to test your understanding. First, if a house is heated and has normal air leakage, does the number of moles of air inside change? Think about how the ideal gas law applies when pressure and volume are constant, but temperature increases. Second, why is it technically incorrect to use the standard volume expansion equation for gases? Reflect on our discussion about the lack of an initial equilibrium volume for gas samples. Use the relationships we discussed today to explain your answers.